Patrick and Jake. This is my new screencast for Module 3, and today I will be talking about missing data and exploratory data analysis, also known as EDA. So the first thing I'm going to do is I'm going to go ahead and read in the data, which I obtained from a lab mate, and he had participants come in and they did a dice rolling task where they were able to lie or tell the truth, and he recorded the mean reaction time for telling the truth, mean reaction time for telling the lie, the difference between those means, and the total number of lies. And then participants also filled out the RT-MITE scale, which is an empathy scale, the MCSDS, which is a social desirability scale, and then a whole bunch of subscales that are all part of the elementary psychopathy assessment, which we do have a total sum here for. So the first thing I'm going to do is I'm going to go ahead and remove the subject ID column, because it's really irrelevant. All these participants were run within relatively the same time period. And then I'm going to move on to missing data. So missing data is missing information that may or may not have been intended to be collected. And missing data can lead to threats to validity, overconfidence, and a narrowed explanation of findings. Some prevention strategies, which are really important for missing data, include a strong research design and one that maybe includes less opportunity for dropout and error. Adding in multiple sessions where subjects have to come in over and over again can obviously lead to a higher rate of missing data. Or even your measurement, including one that has less possibility for error within the measure and insurance that you're measuring what you want can help to prevent missing data. And then also proper data handling is a really good prevention strategy, such as less manual data entry, which can lead to human error and missing data. So for this module, I'm going to focus on treating missing data because it's already there, and this data was actually awesome because, as you can see, there already was one participant who completed the dice lying task and the first two scales, but then none of the EPA. So we have no total score for them. So this is really due to the fact that the participant just randomly had to leave the experiment. They were just unable to finish unexpectedly. So this is really missing at random data, so we can safely omit the missing data. The randomness points to the idea that it's not going to bias our sample. But there are a few ways of dealing with this, and those include deletion, imputation, and adjustment procedures. A possible imputation procedure that we could use would be mean insertion, in which we would just insert the mean EPA score in for this individual. However, because there's such a large range of scores within here, that's probably not the best idea. The best idea is probably to use a deletion procedure. In this case, we could use a pairwise deletion procedure, which really involves just picking and choosing the data that fits and won't be harmful to your data, or a listwise deletion where you can remove participants with any missing data. So because the EPA is very important in regards to looking for correlations within this study, I'm going to go ahead and use a listwise deletion for subject number 7. So you can go ahead and do that with this R code, and then we can see here that it skips from 6 to 8, so that participant has been completely removed from the data sheet. In the report of this data, I would include the statement that one participant was removed from the data due to an unexpected incident that prevented the participant from completing the session and being able to fill out these important measures. Okay. Next, I'm going to move on to exploratory data analysis. So EDA is really exactly what it sounds like. It is exploring your data to look for problems or meaning beyond what the data is presenting. And it's really an important part of all experimental data analysis. And there are many ways to go about exploring your data. One of these is through simply looking at descriptive statistics, which is one of the first things I'm going to do. But before I do this, I'm going to go ahead and condense my data to include columns 1 to 6 and then column 25, because as you look in here, we have the data that pertains to the task and then these two measures, and then all of these measures really are just feeding into this total score. So we can remove all of this in between stuff. So we can go ahead and do that. While I'm doing this, I'm also going to go ahead and round my data. An article by Ehrenberg in 1977 cautions about the pitfalls of rounding, but also provides some detail as to properly round so that the reader can take in more information by being directly pointed to the most important part of the numbers without loss of the data. An article by Weiner in 1984 also included having a million decimal places as one of the dirty dozen rules for displaying data badly, which was an article I really enjoyed reading. So because we are dealing with reaction times in this data, which are likely all fairly similar to each other, it is important not to round too much and end up losing important data. But for simplicity's sake and the reasons stated in the Ehrenberg and Weiner papers, I'm going to round to 2 decimal places. So we can go ahead and view that now. So now we have this beautiful 7-section chart with 2 decimal place rounding, and it's a lot easier to take in and to read. You can really catch it all with one look. So the next thing I'm going to do is look at the descriptive statistics. So one easy way to do this is to just have them written out as such. So this is a good way to get your minimum and maximum values, your quartiles, and your median and mean. And this can provide a decent amount of information, but an easier way to look at the distribution of your data may be to look at box plots and histograms. So I'm going to go ahead and pull up the box plots, and this is them. Sorry that there was that chart over there, I didn't really realize that. But here is the box plots for all of them. We can zoom in on this and we can see that these are all really squishy, so I'm going to pull those up separately because they all deal with 0 to 5 seconds, whereas these deal with values upwards of 200. But just kind of looking at this, we can see kind of looks like they look okay. A few outliers. Median's relatively centered, especially with this EPA total sum, which is really good because that's one of the most important ones. As well, the total-wise doesn't look too bad, so that's really important too. I'm going to go ahead and pull up those reaction times and mean differences separately so we can look at those. So we can see we do have 2 outliers for the mean truth reaction time, and they are all at the upper end. So this means that the participant took a significantly longer amount of time. And we can pull up mean reaction time for the lies. Again, we have kind of a similar situation. And then we can look at the box plot for the difference between the mean truth and mean lie reaction times. And we can see that we actually have an outlier on the negative end here, which is pointing to the idea that since the difference between the means is calculated from the truth reaction time subtracted from the lie reaction time, this one particular participant actually took a longer time to tell the truth than to lie, which is a little bit abnormal, significantly longer time. So that points to some things. We can see we have some outliers. What we can do in this situation is we can go ahead and look at the histograms to really get an idea of how this may be affecting the shape of our data. So we can go ahead and pull up some of these, especially for the truth reaction time and lie reaction time, so we can see that the outlier is skewing our data, pulling the tail out to the right. And we can see the same thing with the mean lie reaction time. That is a similar situation. So again, this person took a significantly longer time to react and make a decision. With reaction times, we are importantly looking for ridiculously fast times because this could indicate simple clicking with no thought, which would be obviously bad for our data. However, an article by Ratcliffe in 1993 also cautions that these particularly long reaction times could possibly indicate a participant's guess based on a failure to reach a decision. So the article also notes how it is important to properly deal with this data so as not to affect our outcomes. And we will get another view of this when we look at the scatter plots. But we will continue with the histograms for now. We can see that the difference between means is fairly normal, which is great, because even more so than singularly lie or truth reaction time, this is important to our data. We can look at the total lies, which is also fairly normal. Empathy scale, which is a little skewed to the right, and the social desirability scale, which is kind of weird. And then the EPA total sum, which is fairly normal, so that's a good thing too. So because the difference between means is fairly normal, the reaction time outliers are probably not super threatening to our data. However, an article by Rasmussen in 1991 suggests that parametric analysis of outlier corrected data may be more powerful than parametric analysis of raw data, or even non-parametric analysis. So that's something to consider when continuing with this data. But it's never a bad idea to start with the raw data, which is what I'm going to continue with today. So a second way to explore your data is to use some graphs. So because this specific experiment is dealing with looking for correlations, I'm going to be looking at some different ways to view these correlations. So first we can pull up a really nice chart, which is very nicely situated. One of the other dirty dozen listed by Weiner in 1984 for displaying bad data is having them organized well in charts. And I really like the way that R has outputted this, because it has all the data dealing with the lie task here, and then it has these two scales that were separate, and then the EPA total here. And I think that gives a really easy way to visualize this. So that's great. Next, we can look at a correlational scatter plot with these significant correlations listed. So that's another really good way to look at things. I have a lot to say about this graph. Whilst I love it, there are some huge problems. This graph is truly a paradox in reference, again, to the dirty dozen listed in the Weiner article for badly displaying data. And one of these dirty dozen explained is emphasizing the trivial. And I particularly like this graph because it literally minimizes the font of the trivial and makes larger the font of the important. So this makes a great display for easily viewing the general important parts of the data. You can see that it has the really significant correlations big and bolded and with a bunch of stars, and then you can see these not even visible correlations here that are kind of starred, but you can hardly see them. So this is something I very much dislike about the graph. It is very difficult to see, which is a huge problem and falls in line with the Weiner's bad display rule number 2, which is hide what data you do show. And in this situation, this is really what's happening. The most significant correlations are large and bolded and with stars by them, while really low correlations aren't even shown, and anything below super significant is in such tiny font that you really can't even see it. So that is definitely a pitfall of this graph. You can still kind of look at the correlations in the scatter plots. You can see that this is a slight negative correlation that probably has a little 1 star there. Same with the empathy and EPA total. You can see a couple of those. So this is a good start to looking at some relationships between our data. So we can still look at some of the most prominent stats figures, especially within the scatter plots. But an easier way to view the correlations will be with this next correlational scale plot, which I really like. This is my favorite. So this is again ordered really nicely. It's got this nice staircase stepping so you're not overwhelmed with a million numbers, and it even has colors that are signifying the level of correlation so they really stick out to you. So this is an awesome way to be looking at this. So from this, we can actually look at more in depth some of the relationships going on here. One of the things we can see obviously is this very high 0.9 correlation between the mean truth reaction time and the mean lie reaction time. And this really does make sense because although they are going to be different, as one increases, most likely the other is as well, and same with decreasing. So although there will still be a difference between these means, they are very highly correlated, and that definitely makes sense. Another one we can look at is the relationship between the difference between the means and the mean truth reaction time, and this is at a negative 0.31. And this makes sense because the difference between the means is again found by subtracting the truth reaction time from the lie reaction time. So as the truth reaction time increases, the differences between the means is going to decrease. We can also look at the difference between means of lying and telling the truth and the total number of lies told. This is very interesting. This is at a negative 0.3, and this is saying that as the distance between lying and telling the truth reaction time decreases, the total number of lies told increases. And this makes sense because people who are telling more lies have more similar reaction times between lying and telling the truth, so that's pretty cool. We can also look at the EPA total and the difference between means, and this is at a negative 0.31. That's a very interesting thing. I'm not entirely sure what to think about that, but that is an interesting thing and is not problematic. It's just saying something else beyond our data. And then we can also look at the EPA total and the empathy scale, and this is at a negative 0.41, which also makes sense because as empathy is increasing, the score on psychopathy is decreasing. So that definitely makes sense, and that's a good thing that that has a negative relationship. So that's some pretty good exploration of our data. To conclude, exploring this data has shown some promising findings, but some transformations may want to be considered to deal with fewer outliers. And that concludes my Module 3 screencast. Thank you both so much for watching, and thank you both also for a wonderful semester. I learned so much and really had a great time in your class, and I really hope to see you both over the summer.